A very good morning to all of you. I welcome you all for this engineering thermodynamics course. And today's classroom discussion topic is comparison of Otto cycle, diesel cycle and dual cycle for same compression ratio, heat rejection and same maximum temperature values. And the motivation behind this particular topic should be known to you. So it is important to compare the Otto cycle, diesel cycle, dual cycle for same compression ratio, heat rejection and same maximum temperature to analyze the cycle performances. That is, which cycle is best under the given condition. So that is whether it is the Otto cycle or diesel cycle or dual cycle for a given condition of the compression ratio or for a given condition of the same maximum temperature and for the same amount of the heat rejection, which cycle will give you the best results. So that is the motivation for this particular class. And the lecture learning outcome is after completion of this lecture, you should be able to compare Otto cycle, diesel cycle, dual cycle for same compression ratio, heat rejection and same maximum temperature. So now let us have the comparison of the Otto cycle, diesel cycle and the dual cycle. So let us take the first parameter, that is the for same compression ratio and the same heat input. So now it is very important one that how can you plot the PV diagram and TS diagram of Otto cycle, diesel cycle and dual cycle. First of all, you should be familiar with the representation of Otto cycle, diesel cycle and dual cycles on PV and TS diagrams because the areas are very important one. So which area, that is in which cycle the area is more, so automatically that will give you the more efficiency. So that's why it is very important to plot the schematic diagrams of the Otto cycle, diesel cycle, dual cycle on PV diagram as well as on the TS diagrams. So now is given the important condition that for the same compression ratio and similarly for the same heat input. So now for the same compression ratio means here, so 1 to 2, so it is the compression ratio. So the compression ratio should be same for the Otto cycle, diesel cycle as well as for the dual cycle. So by keeping the same compression ratio, how can you plot these three different cycles? So now here I have drawn the three different cycles on PV and TS diagram. So here to avoid the confusion I have written very clearly. So which one is representing what? So 1, 2, 3 double dash 4 double dash. So it is 1, 2, 3 double dash 4 double dash 1. So this is representing the Otto cycle. That is the compression ratio is same. So 1, 2, 2 will remain same. And after the compression, the constant volume heat addition is taking place in the Otto cycle. That is the 2 to 3 double dash. The same thing is represented here, 2 to 3 double dash. It is Otto cycle. So next one is the 3 double dash to 4 double dash. It is isentropic expansion process is taking place. Is a 3 double dash to 4 double dash isentropic expansion process take in the expansion stroke. Next 4 double dash to 1, it is a constant volume heat rejection in the exhaust stroke. So it is the representation of the Otto cycle on PV and TS diagram. Next we will concentrate on the diesel cycle. So for the diesel cycle also the compression ratio should not vary. So it is a 1 to 2. So in the diesel cycle after the compression stroke, the next one is the constant pressure heat addition process. So that's why it is a 2 to 3. It is a constant pressure heat addition process. So 2 to 3, it is a constant pressure heat addition process here. You are able to see 2 to 3 constant pressure heat addition process. Next is a 3 to 4. It is the expansion process is taking place in the expansion stroke. Next 4 to 1. So it is also the exhaust stroke. So always here you have to remember for all the three cycles 1 to 2 should be common. Why? Because the same compression ratio. And similarly here all these points 4, 4 dash and 4 double dash 1, all these points should lie on the same line because the same heat rejection or the same heat rejection in the exhaust stroke. So the compression stroke and exhaust stroke are similar for all these three cycles. So always you have to keep it in mind, these two important points while you are drawing this Otto, diesel and dual. That is you are superimposing all these three cycles on this PV and TS diagrams. So next is a dual cycle. So 1 to 2 is a compression ratio will remain same. And next one is a partly heat addition is according to the constant volume 2 to 2 dash. And next one the 2 dash to 3 dash it is a partly heat addition according to the constant pressure. So the same thing 2 to 2 dash according to the constant value. 2 dash to 3 dash is according to constant pressure. Next 4, 4 dash and 4 double dash, all these lines or points are falling on the same line because it is the same heat rejection and it is the same compression ratio. So now we know that efficiency is nothing but is the work done by the heat supplied, but the work done is nothing but heat supplied minus heat rejected. So whenever we are writing down the efficiency in terms of heat supplied and heat rejected, so it is 1 minus heat rejected by it's the heat supplied. 1 minus heat rejected by is the heat supplied. So now automatically since all the cycles reject their heat at the same specific value, process line from state 4 to 1, because I've already told you that all this is the same heat rejection. So the quantity of heat rejected from each cycle is represented by the appropriate area under the line 4 to 1 on the TS diagram. So it is the area of, this is the area, it is the heat rejection. So it is the area, it is the Otto cycle, diesel cycle, because this is the Otto cycle heat rejection. And this is the dual cycle heat rejection, and this is the diesel cycle heat rejection. So it is evident from the equation that the cycle which has the least heat rejected will have the highest efficiency. The cycle which is rejecting the less amount of the heat will be having the more amount of the efficiency. So now just you compare here. So this is having the less area. It is having the less area of the heat rejection. So what is this cycle? Because this is the Otto cycle. So the Otto cycle will have the higher efficiency. Then next one, which one is having the lesser amount of the heat rejection? So this is the dual cycle. So that's why the intermediate one is a dual cycle and the last one is the diesel cycle. So in the diesel cycle, we are having the larger area of the heat rejection. So that's why we are able to say that Otto cycle is the most efficient one compared to the dual cycle and the diesel cycle while operating between the same compression ratio and for the same amount of the heat rejection. So that is a very, very important conclusion we are able to derive. That is, whenever all these three cycles are operating for the same compression ratio, which one is the best one? So which one is the best one? Otto cycle is the best one. And which one will give you the least performance? That is the diesel cycle will give you the least performance. So that is the conclusion which we are able to get it from this important point. So the next important point is, because now you compared according to the compression ratio. Now the second parameter here we have to compare here is for same constant maximum pressure and the heat rejection value also will remain same. So for the same constant maximum temperature and for the same constant volume of the heat rejection, so which one is efficient one? So now how to draw the Otto cycle, diesel cycle and dual combustion cycle for this particular one? So here you can see, so 1 to 2, so this is 1 to 2, so 2 to 3, it is a, so it is a 1 to 2, it is a Otto cycle now here, 1 to 2. 1 to 2. Next one, it is a constant value heat addition 2 to 3 dash. So it is a 2 to is a 3 dash. So next one is a 3 dash 2 is a 4 dash is a expansion process, and 4 dash to 1 it is a constant volume heat rejection process. So next one you are able to see here, that is the diesel cycle as well as the dual combustion cycle. So from this particular one, so we are able to say that the diesel cycle is more efficient than Otto cycle for the condition of the maximum pressure and heat supplied, because just to compare the areas. By comparing the areas only, we are able to say that here the diesel cycle is much more efficient than the dual cycle and on Otto cycle. So here the best one is the diesel cycle, the second one is the dual cycle, and the least preferred one is the Otto cycle for the given condition of the constant maximum pressure and the heat rejection. So that is for the compression ratio, for the same compression ratio, Otto cycle is superior. and for the same constant maximum pressure, the diesel cycle is the superior, and the dual cycle is always lying in between the Otto cycle and the diesel cycle for the same given parameters. So like that, we are able to compare the Otto, diesel and dual cycle based upon the same compression ratio and same heat rejection and the same maximum temperature and same heat rejection. So like that, we are able to conclude. So which one is giving you the more efficient results for the given possible conditions. So thank you one and all for attending this lecture and listening very carefully about the performance comparison of Otto, diesel and dual cycle. Thank you.